In the homework you just gave me, you were asked to solve a bunch of stuff. Because we had delineated each chapter, separable, linear, exact, you know what techniques to look for, right? But if I gave you an arbitrary differential equation and said, solve this, well, then I'd want to know which of those three patterns it matched. Is it separable? Is it linear? Is it exact? Maybe I can solve it more than one way. But as long as I can identify a way to solve it, I'm really pattern matching. Sometimes it just don't match. Well, then I start to think about what could I do instead? Rather than develop a whole brand new technique, rather than come up with some absolutely cockamamie idea, I start thinking about, well, what would be close? What tweak can I make to make this into a pattern I want? And there are several substitution methods that work, provided I have certain hypotheses. So let's consider a first-order differential equation. I've written it in its standard form, y prime all alone. If I'm lucky, then I can find an equation y equals something of x. But maybe I can't. What if I say, all right, I'm going to throw in a dummy variable. And instead of thinking of y as just a function of x, let's think of y as a function, my solution equation. Let's think of y as a function of two variables. That is, I'm going to screw this up over and over. Instead of thinking of y as a function of one variable, let's think of y as a function of two variables. Every time I start to write the y and the u in the same equation, I want to make them both y's. I apologize. But I'm just going to use this u as a placeholder for some other function of x. So really, I'm saying this is actually a composite function. Hey, wait a minute. Now I know why they're calling it substitutions, because that was what we did with u substitutions. I deal with composition. So I'm thinking that this u is the same u as in a u sub, but I don't know what this u is supposed to be. If I have this version of y instead of this version, and I wanted dy dx, then I would use the chain rule based on Calc 3. The Calc 3 version of the chain rule, because y is g of two variables. So I would need the partial derivative of g with respect to x times the derivative of x with respect to x, and I would need the partial of g with respect to u times du dx. Wait a second. Dx, what's that? That's 1. So really this is this. And over here, I have this thing, right? dy dx. But my original differential equation was about dy dx, wasn't it? way back up here. This is y prime. Let's put that on the left side. That would be f of x, y. But y is a function of x and u. So notice this is now related to x and g and u. So I have a little bit more complicated of a thing here, right? I made my equation a little uglier, messed with it a little. But now I say to myself, what if I tried to solve for this derivative? Because you'll notice the only derivative in this equation now is du dx. If I can figure out a differential equation involving du dx, maybe I can solve that one. So I've turned my original equation about y into a new equation about u. But these are all in terms of x and u on this side, right? I know there are two variables there, Gesundheit, but I'm really only thinking about u as my y variable. This is a brand new differential equation. Du dx is some function involving x and u. That's a first order equation. If I can solve this, then I can back up and solve for y. So this additional substitution comes around, and I can make my life easier, I hope. It now is though a two-stage solution, right? Because now I have to solve for u first, and then I have to solve for y. It turns out there are a lot of special cases where this works under certain conditions about the equations. It's going to depend on our functions. So I need a new definition. A function of two variables is homogeneous of order alpha. Gesundheit. Wait a minute. I've heard that word before. Homogeneous. Where did we use that word before? Courses I know you've taken. Linear. We talked about homogeneous systems of equations, but it meant they were of the same form, right? They were all set up equal to zero. That was what homogeneous meant for linear. They were of the same form. I want to think of this being homogeneous as in the variables are of the same form if f of tx, ty, I multiply by t in there, becomes t to the alpha times the original function. Now, before you look at me like I've lost my goddamn mind, you've seen this before. Here's a function. F of xy equals square root of x squared plus y squared. I claim this is a homogeneous function. Let's check. Replace each x by a tx and each y by a ty. What do you get? What happens with this expression on the right? I can't separate the squares and the square roots like that. I can't take the square root of each piece. I can't distribute that square root. So it's okay. Not an uncommon first reaction. If I multiply it out, the tx all squared becomes t squared x squared. And the same thing happens with the y. So this is t squared x squared plus t squared y squared, all under a square root. Now remember, my definition of homogeneous talks about pulling those t's out. I've got a common factor. So let's take it out. This is the square root of t squared, x squared plus y squared. Hey, wait a minute. Now, I'm multiplying in my square root. Now I can split it up. Now I can write it as the square root of t squared, square root of x squared plus y squared. But what's the square root of t squared? Well, isn't that nice? It's t to the first power times the original equation, square root of x squared plus y squared. This is t times f of xy. This is homogeneous of order 1. You with me so far? You can have functions that are homogeneous of order -1. You can have functions that are of homogeneous of order 3, 5, 2.5. You can have functions that are homogeneous of all sorts of orders. For example, f of xy equals x minus 2y over 3x plus y is homogeneous of order 0. Because if I put a t in on top in all of the variables and on the bottom in all of the variables, aren't all those t's going to cancel out? And I'll be left with no t's at all. F of xy equals 1 over x cubed plus y cubed is homogeneous of order -3. Oh, that should be a y cubed, not a y squared. Y cubed. You said it one way, but I wrote another. Not do that. You should check, make sure I'm not talking out my ass here. Leave yourself a little room and check that later. A differential equation is homogeneous if the component functions are homogeneous. A differential equation, m dx plus n dy equals 0. Hey, wait a minute, that's the setup for exact, right? But if it isn't exact, I could be in trouble doing this. I might have to try and find an integrating factor. I might not be able to. Or I might get lucky and m and n are both homogeneous. One of the other textbooks I was working with didn't write homogeneous this way. They decided to pick one of the variables, X or Y, and divide by it. So I'm either going to do X over Y, I'm going to do Y over X. Which way do you want to do it? X over Y or Y over X? X over Y? If I do X over Y, let's call that V. I'll make a V substitution. Well, then I can think of this behavior. It's for N. N xy is equal to y to the alpha n v1. Because if I make that substitution, then I can think of x to any power as v to that power y to the power, and I can take the y out based on my homogeneity. For both functions, m xy equals y to the alpha m v1. If we do it the other way around and do y over x, what I really did was I substituted dy for x. If I write y over x, let's call that u. That's the same as saying y is x times u. Well, then my rearrangement is that m of xy is x to the alpha m1u. It goes in the other spot. And n is x to the alpha n1u. That means if my functions are homogeneous, if m and n are both homogeneous of the same alpha, I can use one of these substitutions. And if I'm lucky, the result is separable. Not just exact or linear, but separable. That's a hell of a claim. So let's see it in action. Is this exact? You just did this in the homework. How do you know if this is exact? How do you know? Partial with respect to y. Okay, so that's 2y plus x. Take the partial of x with respect to x, you get negative 2x. Negative 2x. Those are not the same. It's not exact. If I really want to try and bust my butt, I could say, well, let's see if we can find an integrating factor, which is what we did on the homework, right? But I have to hope that the integrating factor has all x's or all y's. But Cody, what you said is you said this is M. And this is N. Are these functions homogeneous? If you put tx and ty in there instead of x and y, and you pull out a power of t, it's the same power for both of them. Yeah. If I do m of tx, ty, I get ty quantity squared plus ty times tx. Well, that means there's a t squared y squared and t squared yx, and that's t squared times the original thing, isn't it? And over here, if I do n of tx, ty, I get minus the quantity tx squared. That's minus t squared x squared, which is t squared times the original thing. These are both homogeneous of order 2. In linear, we used the idea of homogeneous to talk about the form of the equations. They were all linear equations, number x, number x, number x equals 0. Here I'm using it to think of the powers involved. Each of these 3 pieces, y squared, yx, and minus x squared, they're all basically squares. They're quadratic. I have x times x, I have y times y, I have an x times a y. They're all quadratic. So while this isn't exact, it is homogeneous. I'm going to use one of my substitutions. We can either use U or V. Coin flip, U. U is y over x, or ux equals y. I want to use that in the equation. Houston, we have a problem. I don't just have x's and y's up there. Up there in the original equation. Not even worried about t, but up there in the original equation, I don't just have x's and y's. I have dx and dy. I can take the derivative of this to get dy in terms of u and x. Product rule. dy is derivative of the first times the second. du. Then derivative of the second times the first. Product rule. Now, let's put these into our equation. Everywhere you see a y, write a ux. Everywhere you see a dy, write this ugly mother. Well, isn't that just thrilling looking? Are you ready for the best part? Multiply it out. Tell me what you get. Ux quantity squared becomes u squared x squared, and that's times dx. Ux times x is ux squared, also times dx. That multiplies out all these terms over here. Over here, I subtract x squared times x times du, that's x cubed du, and then x squared times u dx. That's here. What wonderful thing happens? I can cancel what? Yeah. Plus ux squared dx minus ux squared dx. Those are gone. The result is u squared x squared dx minus x cubed du equals 0. Now, before you run screaming for the hills, that's separable. Put all the x's on one side and all the u's on the other. It worked. I have to start by putting the u and the du on, the dx and the du on opposite sides. So I have u squared x squared dx equals x cubed du. Then I'll put the u's on the right and the x's on the left. What do I get?
For x dx equals one. Where do you?
Ta-da! You know how to solve that, don't you? Remember, we're thinking of u as a function of x. X is the independent variable, u is the dependent variable. So when I integrate this, I get negative u to the negative 1 equals ln absolute value of x plus c. I put the plus c on the independent variable side. That's why I made you think about it. Oh, move the minus sign over and flip this because this is minus 1 over u. That means that u equals minus 1 over ln absolute value of x plus c. What was my relationship between u, x, and y?
Y over x.
So y is u times x. That makes it negative x over ln absolute x plus c. We just solved our differential equation. The one that wasn't exact, Cody, that I couldn't solve because it wasn't exact. And instead of finding an integrating factor, I did a u substitution and reduced it to a separable equation. My substitution took me to something substantially easier to do. By the way, if you instead of using u had used the v substitution, you'd get the same answer. You just have to do a little algebra to show that they're two the same. By the way, how did I decide which one to do? I did a coin flip, right? But really, I can go back and I can look. And I can say which one of these two expressions is simpler. If this one is simpler, do the substitution on y. If this one is simpler, do the substitution on x. So you substitute for the letter that is with the simpler one, the differential. Because I really needed the dy in terms of the easier things. But once you start doing this, if you get to a point where the integrals absolutely suck, back up and do it the other way. Questions?
Where'd that negative x?
Ah, it's a -1, right? Y is equal to u times x. They just multiplied in the x. You were the one that said this is the substitution, right? No, you were the one that said it was y over x. That means the y is equal to u times x, multiply the x in. Another interesting thing, please notice the plus c appears in the denominator here, as opposed to off on the end. You have to make sure you put your plus c in at the appropriate time when you integrate, so that it ends up in the right place in the problem. More questions? The heyday of differential equations is the real growth in the study of electromagnetics, which is the late 1700s, early 1800s. So you get a lot of big names, people we recognize, who have done a lot of mathematical physics studying differential equations. People like the Bernoulli family. Those of you that took the readings course, we talked about the fastest descent, the tautochrone and the brachistochrone. Those were the Bernoulli problems. They were studying physics of sliding objects. Well, a bunch of differential equations came up in those sorts of things. And in particular, there's a whole class called Bernoulli equations that are almost linear. That's what a linear equation is supposed to be, right? Bernoulli equations have an extra factor of y to some power on the other side. They're nonlinear. If n is 0, this is a linear equation. But if n is anything else, well, if n is 1, then it would be separable. Because then I could combine this y to the first with this y to the first. But if it's bigger than that, then I have a problem. And Bernoulli said, I hate this. This is atrocious. It's a pain in the ass. I don't like it. I'd rather get rid of it. So when Bernoulli generalized this idea, he said, I'm going to use a substitution. And the substitution I'm going to use is u equals y to the 1 minus n. The result when I do that is actually linear. By the way, the first person to do this wasn't actually a Bernoulli. The first person to show an equation with this sort of substitution worked was Leibniz. But he only did one case. Bernoulli generalized it, and that's why he gets credit. We also find it easiest because you'll notice y is 1 minus n. That means I'm going to have y to negative powers. So we find it easiest to divide this y to the n over first. An example. Now, this doesn't look like it's in the right setup at the moment. But it turns out, again, a little bit of algebra here. This right-hand side is xy to the fourth minus y. And this right side is a y prime. If I move this y over here, I have y prime plus y equals xy to the fourth. If it was just an x on the right-hand side, this would be linear. But it's not. That y to the fourth is in the way. So according to Bernoulli, what's my substitution? I want to use u equals something with y. Y to the... It's off the top of my screen here. What was the formula for the substitution here? And n is the power over here. So it'll be 1 minus 4 or y to the negative 3. But before I do that substitution, I divide by y to the fourth. Y prime times y to the negative 4 plus y divided by y to the fourth is y to the negative 3 equals x. Wait a minute. Wait a minute. Wait a second here. If this is my substitution, what's du dx? Just from here. What's du dx? But wait, there's more. That would be the derivative in terms of y. I was asking for the derivative in terms of x. So I have the chain rule. dy dx. Or solve that for dy dx. dy dx equals, I got to divide by this stuff. So that's negative 1/3 y to the fourth du dx. Now you're looking at me like I'm an alien. I understand that. But watch what happens when I do these substitutions over there. Y prime. Y prime is right here. Write down y prime. Then there's a y to the minus fourth. Y to the negative 3, that's U. What happens with all of this mosh over here? In that left term, what happens in that leftmost term, Jack? Or multiply through by negative 3. At which point, I hear in the back of my head, son of a, that's linear. It's linear in U, not in Y. It's linear. But once you get U, you can solve for Y because you have our substitution. U equals Y to the negative 3. So once you know what U is, and you know how to do that one, you know what Y is. You took the ugly, not easy to do equation, made a weird substitution, and out popped an easy equation that not only do you know how to do, you've already done. I'm going to leave room. You should leave room to finish this. You need about another 8 or 9 lines to do all the calculus. Find the integrating factor, e to the integral p of x, do the integration by parts on the right-hand side. You can do this. You should get that. Once you get that, you know how to get y. You're done. So I found a way to take an ugly equation and reduce it to a separable equation using the x over y or y over x trick. That only works for homogeneous equations. I found a way to take an ugly equation and reduce it to a linear equation. So I found a way to do separable, linear. I found a way to do separable. There really isn't a good way of dealing with exact, reducing something to exact, except for our integrating factors. But again, there are other forms. If I have some function on the right-hand side that mixes my a's and b, my x's and y's together in a nonlinear way, some function that mashes up x and y and constants, like this. Bleh. That's gross, right? I hate that thing under the square root. but it's linear, as in everything is to the first power. Not linear like the linear differential equation. It's linear in the original sense of linear, first powers, under the square root. Like it shows right here. Number X, number Y, number alone. Number X, number Y, number alone. Let's use that for a U substitution. Wait a second. If that's my U substitution, what's du? It's du dx. Du dx, just like we have dy dx. What's du dx? I'm still using x as my independent variable. But wait, there's more. There's no u on this side. Say, here, I need that dy dx. Wait a second. This is u. So what's the right-hand side here? What's the left side? Cancel the twos. This is a separable equation. That's trivial to solve. I know how to do that. We did that one last Friday. I know how to do this. Back when we did integrals in Calc 2, in chapter 7, where we did all these messed up different techniques of integration, right? We said, maybe it's a U sub, maybe it's parts, maybe it's trig, maybe it's a trig substitution, maybe it's partial fraction. And then we got to, maybe I need to do something weird. Differential equations evolved exactly the same way. And there are literally dozens of individual cases where somebody noticed, hey, this trick works in this kind of equation. And as time went on, people found more and more places where that trick worked. That's how we got these gross categories of techniques like separable and linear and exact, because we were able to find a whole class of equations where these techniques worked. Well, now I have a couple of one-shot. What happens when these don't work? We'll talk about that on Monday. So I will see you all then. I hope you have a wonderful rest of your day and enjoy your weekend. If you came in late, please come bring me your homework. I will see you all on Monday.